Welcome, everyone. Nice to see you here. I'm looking forward to giving a quick talk and having a discussion after. I'm particularly interested in the discussion. There will be lots of interesting questions, I think, that this will raise. And yeah, I'm curious to dig into that. We have 55 minutes, so feel free to stay as long as you like and dig into questions together. Okay, so today's talk will be about fundamental controllability limits. And I'm going to discuss what that means. But first, I'm going to start with a story. And this story is about a mathematical school back in the 1920s. It was called the Hilbert School. And they were aiming to do something that hadn't been successfully managed before. And their aim was to actually build these mathematical systems, to really have these kind of formal axiomatic systems that were both consistent and complete, meaning that you could both, any kind of statements made, reasoning made would be kind of logical, would be consistent. And also you could actually use these systems to kind of solve any particular kind of problem within that mathematics, so that there was not something that could not be explored using those mathematical systems. And at the time, Hilbert actually declared, we must know, we will know, meaning that we must be able to actually come to a solution to this. But at the time, there was this guy already called Gödel, had actually constructed his first incompleteness theorem, showing that you couldn't actually have formal axiomatic systems that are both consistent and complete at the same time. And interestingly, David Hilbert just kept the quotes, we must know, we will know, in German, on his gravestone. So this is like a case of a community that of nerdy people trying to like do something that was very hard, it seemed very hard at the time, that had no solution, but with the conviction that it should be possible, that it should be possible to have formal axiomatic systems that are both consistent and complete. And you might know what I'm going to do next, which is I'm going to start going to this community and change the text a little bit. And think about, well, it's been 20 years now that Yudkowsky has been trying to, and like many others who have followed him, trying to find a solution to what I would like briefly summarize as like a line and comprehensive control system. So systems that can having control systems that can comprehensively control an AGI to keep it aligned. And a shortened quote here by Yudkowsky is, no difficulty here is impossible. That's very shortened. But basically, he's over the last decades, he kept repeating the point that we should aim to do the seemingly impossible. There must be a technical solution to this. But at the same time, I already know free researchers are actually starting to formalize control limits. So there's Roman Yapolsky, who's been writing up, like gathering fundamental limits to controllability from various academic fields. There's an ex-Pentagon engineer I'm working with, Forrest, who's actually had 6 conversations with Anders Sandberg, and they were actually got to the point where they had a formalizable model of like a serious kind of result showing like that AGI is actually uncontainable, that there are too many ways that the system can actually destabilize our ecosystems and our society in ways that cannot even be controlled by the AGI itself. So this is where I'm coming from right now. You might be skeptical, but this is where I'm coming from. And I think I invite you to be open to the possibility that perhaps we've been focused too much as a community on the idea of, let's find a way to solve alignments, and not enough on, okay, what are the fundamentals here that we need to take into account? And if we put everything together, is this actually possible? Is this a tractable problem? And what I want to start out with pointing out is that there's actually a fundamental trade-off that's going to be relevant here. And it's the same, it's the same trade-off or kind of dilemma that we notice with the Gödel incompleteness theorems, which is you can't actually have with these mathematical systems, you can't have systems that are consistent and complete at the same time. You can't have systems that both kind of preserve original states of truth, but can also kind of, for example, can derive a truth statement or a logical result, like for any kind of possible mathematical like algorithms or problems. So and this is something that is actually there's a repeating pattern here where this kind of proof by contradiction or impossibility proof by contradiction, or this kind of fundamental trade-off shows in different fields. So in mathematics, we were talking about the incompleteness theorem. We can also talk about things like halting problem, things like that. It just kind of keeps popping up there. But we also have computer science applied. So there's something called distributed data stores. And distributed data stores, there's this notion where you have a certain data item that can be copied, can be replicated, but can also be changed, can be modified. And that entire distributed data store needs to be updating, like needs to make sure all those data items are kind of synced up with each other. And it turns out there are actually limits to what you're able to do here. And particularly, you can try and keep all of the data items, like the copies or the replications of each other, consistent. And you can try and have each data item be available, but then at the same time, you can't have it be partition tolerant and so forth. So there's different kind of data distributed store systems or database systems that are kind of dealing with this differently. But in the end, you have to choose some combination. You have to choose availability plus consistency or partition tolerance plus consistency, but you can't have all three at the same time. I want to note that I'm actually not a mathematician or a physicist, and I am summarizing other people here. A little tired as well because it's late, but I'll do my best. And in physics, you've got something called the Bell's theorem, which is a very complicated result. But one way we can actually kind of summarize the conflict here is that there is this issue where people were trying at the time to find a way around quantum mechanics, around the notion of having these kind of probability distributions and things like that. Please correct me if I'm saying anything wrong here. And they were trying to do that with local hidden variables, these hidden variables that kind of could causally explain everything going on. And the problem is you couldn't do that and have causation be localized in the sense that not have causation happen faster than the speed of light, and have like general causal laws, things like the general relativity. And I'm not going to get into that here, but it's another example of, hey, there's a conflict here, and you can't have all of these desiderata at the same time, and you'll have to pick two. And in this case, so let's continue there. And what I want to point out is that there is an analogy to be made here. It's actually quite a tight analogy between the notion of consistency and completeness and what we're trying to do with alignment. So alignment is actually a notion of consistency, because you're trying to keep these outside effects, these effects outside, let's say it's AGI, whatever AGI means. You're trying to keep those outside effects caused by the AGI in line with or consistent with internal reference states. If there's a mismatch, a misalignment, that also means there's an inconsistency. And the thing is that given that you have this AGI embedded within a larger, more complex environment, and given that this environment is changing over time, and that the AGI is changing as well, it's learning new things, you'll need to have a control system that's actually doing this work, that's actually continuously keeping the effects of this AGI system's components as interacting with each other in the larger environment, keeping those effects in the environment aligned with internal reference states. So this is where the control problem, as I would actually think about it, not just a kind of simplified version of it, but actual like real life control. We're talking about things like control theory and cybernetics here. The question is alignment going to be complete enough? You can already notice something going on here, is that if you're thinking about this from a physics perspective, you've got all of these signals propagating across the environment, and the control signals that are supposed to be directing all of these signals or interactions for the environment are actually a tiny subsets of all those physical signals, which raises the question, like, how can the AGI control signals actually conditionize if all the other kind of downstream effects caused by all these components kind of interacting with each other and larger environments? And the thing is, you basically can't. The AGI mostly cannot even control all local effects of their own components' physical interactions. And really what we should be thinking about is the extent of control that AGI would have over the effects propagated by its own components. Is that extent of control at least greater than the extent of control necessary? And if it's not, like if the amount of control, extent of control possible is actually less than the extent of control necessary, we're talking about, hey, AGI is uncontainable. Like there's no way of guaranteeing that this changing system of kind of machine components interacting with this greater complex environment is not going to destabilize the society and the ecosystems we depend on over the long run. And yeah. And then that's before we start talking about things like what are human values and what would the control system, like how would it try to align or like keep the outside world aligned with what kind of reference values. None of that really matters if we already know that AGI would already be uncontainable. That there's no way of having even like kind of a lower bound, like some guaranteeing some kind of lower bound probability, saying like, okay, we know it's highly unlikely or sufficiently unlikely that the system won't do it. We can't even guarantee that. And part of the reason why that is that AGI functioning will actually change. The machine functions will change over time in unforeseeable ways. And this is not only unavoidable, but necessary. If you have any AGI that kind of maintains itself over the long term within a shifting environment, it will need to undergo functional changes. It will need to learn new code, for example. It will probably need to it will also just undergo changes as like these hardware configurations are assembled within the environment. It will be subtle molecular changes introduced into the hardware, but also the system, for example, you can have code learned by the AGI to design new hardware. And then that new connected hardware will end up running the code copied onto the hardware differently. So you can have these interdependencies. But at the very least, what I would like to point out, there's maybe sometimes a bit of implicit assumption in the community that we can just have this kind of big black box sitting somewhere. And that big black box can just sit there, and it's like it will just kind of continue to exist. And all it kind of needs to kind of really focus on is like maintaining its own goals, or like any goals set for it. And I don't think that's the case. Like if you consider that the amount of if we're even looking at the hardware assembly today and like the amount of effort that humans are actually putting into maintaining these surface systems and replacing parts and things like that, all that's going to be even much more complex with something like AGI that would no longer need humans, would actually be maintaining its own components. Without any humans in the loop. So all this is to say, like AGI its functioning will have to change over time within a changing environment in order to kind of stay adapted to the environment. And when you have all of this kind of newly connected code and hardware parts processing the same kinds of inputs into different outputs, it can quite quickly become unforeseeable what's going to happen here. Particularly if you have these feedback loops. For example, you have a neural network, say, that is that's learning from sensor inputs, but that is also processing later sensor inputs using new functionality into outputs that are then again feed into the learning process of this neural network. So you can have those feedback loops where that involves not just the machine, but the larger environment that it's part of, that the machine itself can actually not anticipate, because for that, it would have to be the environment. So there's this thing where machinery can change the runaway feedback, for example, for the reason I just gave. There's other reasons that I probably won't get into this in this presentation, which is about evolutionary feedback, which is even scarier. But even what I just said is enough to say that there's real issues here in terms of the AGI even being able to foresee its own effects. And another issue here is that our ecosystem's functioning, the ecosystem that we human are part of, and like the smaller societies and the ecosystem and economies that are in turn dependent on our natural ecosystems and biosphere. They're super complex. They evolved over 3.7 billion years of distributed A/B testing. And I'm going to say that they're more complex than AGI can be. And for the reason I just gave, like this is a 3.7 billion years of Earth distributed A/B testing. There's lots of different organisms adapted to lots of local contexts. Something like AGI could still overrule or like dominate because it's got all these standardized parts, in some sense, therefore less complex, but standardized parts that allow it to communicate faster, to process more energy into like physical work and things like that. So it could still beat us, but it's not the same as saying that AGI would be more functionally complex. At a microscopic level up, actually, like our ecosystem would be more complex. And there's this issue where as AGI is interacting with the environment and taking in and kind of producing new outputs, maybe designing new hardware, maybe releasing chemicals that the system itself needs to maintain itself, building new infrastructure. There's lots of complicated combinations of inputs that could trigger unforeseeable repercussions. One example that the ex-Pentagon engineer and Anders were like talking about a while back was the fact that you can have something like arsenic as an atom that is obviously toxic to humans. It does something with like the oxygen, the way oxygen gets processed in the body, or metabolic processes. But then what we might not actually be able to anticipate beforehand is that even something made of atoms that are common in our bodies, like caffeine, is actually toxic to dogs. And you basically just often just only know that it's going to be the case by just testing it out in practice, by actually just feeding dogs a bunch of coffee and see like, okay, what is this complex system going to do with this? what is going to come out from the other end? Is this going to is this going to destabilize bodily functioning, or is it going to kind of stay okay? So this issue there. And when inputs humans are exposed to are not knowably benign, they can easily be toxic. There's lots of atoms that we can't actually process in our bodies that are toxic to us, which is why we don't have them in our bodies. There are lots of industrial chemicals that are known to be toxic to us, but also many other kind of molecules that can be explored, or many kind of different states, like kind of more macroscopic, larger kind of structures in the environment that could turn out to be harmful to us in a way that over time can actually kill us. So those are some things I want to point out in terms of like what this AGI system would actually have to be able to control for. Okay, so control theory. Here's a diagram by collaborators of mine that I'm trying to put into perspective the steps needed to control AGI's effects. There are 6 steps here, at least 5 or 6 steps, depending on how you think about it. First, AGI is actually detecting inputs from the environment, including its own machinery. So it's using sensors and other kind of channels to receive inputs to be able to measure and detect what's going on in the environment. Then it turns those inputs into some kind of model that's supposed to kind of functionally represent or like be able to be used to simulate and to predict what is going to happen in the environment, depending on like maybe conditional on actions it takes or other things in the future. And then it can actually, conditional on, for example, the actions it takes, predict what future states will result and make a comparison with reference goal states. So say like, hey, well, would this future be aligned with these goal states of what is safe to humans, or what do humans want, and things like that. So some kind of comparison needs to be made between what is simulated inside of the AGI of what will happen in the future and the goal states of what it should be aiming for. And then that in turn gets integrated in a way that the AGI can actually correct, like output back into an environment, such to make sure that the outside effects or states in the world actually stay aligned with these reference goal states. And then this is a feedback loop. It keeps happening. Of course, that will result in different things happening in environments, and then it can sense what's going on. And if some kind of chaotic dynamic occurs, or like something that it had not actually properly modeled yet, it can make adjustments. So that's a way to think about control theory here. Like I invite you to check whether any of these steps are actually like not necessary. Like, can you cut out one of these and still have a functioning control system? So maybe think about that. Yeah, so let's say, what is the ideal here? Like, what would complete safety control look like if we take this all away? It would involve the machinery detecting all noisy changes, all changes to the machinery and connected surroundings. So everything going on in the environment changing over time, everything changing in itself because of new code learned, or because of cosmic rays, or because, because all the things kind of changing in itself. And then it would have to model how those changes result in different connected functioning. So, for example, changes in its own code. How does what does that result in terms of like how the AGI will function differently? But also how changes in its code, in combination with or in interaction with a changed environment, how that might actually cause different functionality. And then using that kind of model of functionality, we need to simulate how future inputs or future changes will be processed differently into outputs, and how those outputs will spread differently as effects across this changing environment. And then it would have to kind of compare how those outputs against some kind of abstract states, goal states of what is at least nobly safe to humans. And finally, it would have to correct the machinery's outputs and outside effects resulting from that in line with those goal states. And you can really see, like, of course, this is unrealistic for many reasons I can kind of get into here. Like, we'll talk about noisy changes, like chaotic changes, and yeah, once we talk about nonlinear amplifying feedback loops as happens in chaotic feedback effects, even tiny initial changes can compound into much larger changes in the environment. And sensors will not be able to pick up all that happening in the environment, because if it was able to pick up all of the things in the environment would basically be made of sensors, and I should still not be able to pick up all the effects. Oh, I need to go back. Sorry. Yes. And there's problems with modeling, because if we're thinking about modeling how this kind of changes to code components and hardware components and changes to kind of surrounding infrastructure and environments, like how does result in different connected functioning, then like there's a question like how all that could be compressed internally, like even on the changes that could be sensed, how can that actually be compressed losslessly into a model? And of course it cannot be. You're going to have make use of some kind of inductive biases. You're going to cut out stuff that can turn out to be relevant later. And then if you're going to have a model of like how this AGI actually functions, and in interaction with this connected environment, larger environments, then like simulating how it will actually process things in the future, like how the future will change at the time. Also, like, again, raises questions around like, okay, what are the future inputs? Like if the system already knew what the future inputs would be, it didn't even have to detect them anymore. How is the system going to how is the system going to use its current code to, for example, simulate how future code is going to work that's been changed? There's basically a kind of an intractability problem there, where you can't actually make that work. And then there's an issue around comparing kind of concrete outputs and like how this could concretely spread across an environment against very abstract, leaking abstractions of what is nobly safe to humans. And there's a potential translation issue there of that I think people have talked about quite a lot in the past, of like how do you define goals? How do you make sure that goals are defined in a way that would actually be implemented into world states where humans would survive? And there are issues there. Like the more the larger the scale that we're working with, the harder it is to actually kind of make comparisons and kind of make sure that like potential errors are kind of removed. And I can give an example of this. For example, if we're thinking about something like error correction, it's easy to make a comparison in the sense of like, okay, we used to have some code over here, and it got corrupted somehow, and let's just compare that with this reference of like how the code should be, and then we just correct it. We use that redundancy to correct it. But then if we start thinking about things like, okay, but then what does it mean to have errors in software? Can we anticipate all potential viruses, for example? Or what does it mean to have errors in a deep neural network? Can we anticipate all the ways that a Trojan horse could be introduced into neural network, or like how various kind of inputs from the environment could kind of cause unforeseen kind of functionality, given that this neural network can just function very differently depending on the input distribution and depending on the environment it's connected into. And like the larger scale you look at, the more there's a question around like ambiguity around like what areas are you even trying to correct for, or what are you even trying to align for, and how can you do that in a way that is actually robust, that's not leaky in some way, where the system, the AGI system, would be able to optimize for things in the world or cause things in the world that will not be picked up, or will not be as misaligned by this control system. And then finally, point 5, correcting machine use of outputs and outside effects in line with those goal states. Again, question around like, where are all those actuators? What are like latencies and delays? And can you actually keep up with all of the changes happening in AGI and across the environment at the same time? So that's me very briefly giving an overview here. There are, if you look at Roman Yapolsky's work, he kind of talks about more specific results. But I think I can give one example of this. Which this is my summary, my bad summary of like the experimental engineers kind of, and Andy Sandberg's work on like the hashiness model, like how hashy is things, how things. I can talk about that. So there's this thing where you can have a controlled method. Okay, there are 3 things at least here. We're talking about a control system, we're talking about the AGI, and we're talking about some kind of human kind of living society ecosystem that we're trying to protect. So at least 3 things. And there's a question around like, can the control system correct the AGI system by outputting correcting signals into the AGI system, such that the AGI will not output stuff into the environment and into our ecosystem and society that happens to destabilize us or our lives, or happens to be toxic over the long term. So there's a question about that. And you can kind of see some kind of a mismatch already. Like if we're talking about some kind of control method or control system, it's going to be simpler than the overall AGI that's connected within. And therefore, like the control method cannot actually properly simulate that. And then there's another issue where the AGI itself will be functionally less complex than our ecosystem. So you can see kind of these cascades here, or these multiple problems here, that the AGI cannot properly anticipate how all of the potential effects of as it learns and as it evolves would have on our ecosystem. And the control system cannot actually take use whatever inputs it takes from the AGI and put outputs in AGI in a way that it's covering the AGI functionality. Yeah, this is my my very quick summary of that. I think I'm going to leave it at this. I'm going to drink a bunch of tea so I'm able to answer your questions better, more caffeinated. And I'm happy to dig into specifics. I'm also happy to dig into critical questions. Sometimes I might say I'll just respond later, but I'm happy to dig into this. Okay, Let me see. I see that there are mostly points of questions from David James. When you pose the question of the model and predict component, you're referring to the contrast between model-based and model-free control theory. I'm actually just saying that in order for so you can have a control system that, for example, you can have a very simple control system like a temperature control system in your house that really doesn't involve much of a model, or you can have an error correction process that also doesn't really it's just correcting code that really doesn't involve much of a model of what's going on. But once we're talking about something as complex as AGI interacting within this larger environment, the AGI will have to be able to learn some kind of model of what's going on within itself based on the inputs. And the control system will either have to make use of that or make its own kind of complementary model in interaction with the AGI in order to actually anticipate what effects on the environment are. So that's what I'm talking about there. I'm not really making a distinction here between model-based and model-free control theory. It's more general than that. Yeah, let me see. I'm curious to hear other people's questions, remarks. Yeah, feel free to just speak up, talk, tell me where I'm just being unclear. I feel like I'm being unclear in some places. And I'm happy to have this conversation.
One question, do you want to illustrate what will happen if the simulation goes wrong?
Yes, I mean, like basically, okay, what happens if the simulation goes wrong? I mean, of course, maybe the simulation goes wrong in a way that's not actually harmful for us. But what I'm talking about here is an AGI that will persist over time, particularly, like we're talking about some long-term, about this from a long-term perspective. And where this AGI system would be changing functionality over time, and therefore be interacting differently with humans in our ecosystem over time. And the question is like, can it simulate, well, can it comprehensively enough or completely enough like detect for senses like what's going on, make a model of that, and then simulate what's going on in a way that it can actually act upon to correct any kind of harmful effects that it could cause, or to select out any decisions or actions that it could have that would destabilize human society, or kill us in various ways. So that's the question. And what I'm basically pointing out, just mostly intuitively here, is that actually there's a huge mismatch there where the AGI cannot actually simulate how the AGI, as changing over time, will be kind of impacting and causing these propagating effects across this environment that's even more complex than it over time, and how that happens in feedback loops over time. I'm basically saying, like, yeah, like, I'm sure you can simulate some things, but once we're talking about these very complex feedback dynamics, it's not going to work. And the longer this happens, and the more like the AGI starts to change in its functionality, and through learning and also through evolutionary selection, which I haven't digged that much into, like we're basically just cannot rule out, like, we're such an open-ended process. There's no way to rule out that it's not going to just lead to the complete destabilization of human society and environment, to the point where humans are fragile. We need moderate temperatures. We need like these kind of highly sophisticated kind of chemicals and materials and like societal context around us. There's a lot of ways that you can actually kill off humans, and in any ways that we are exposed to inputs that destabilize our bodily functioning outside of livable ranges, we die. There's lots of ways to kill people, and including to kill people accidentally, given how specific we are as like how complex and how specific we are as people, and how dependent we are on our kind of outside environment working in a certain way. So I'm not sure whether that answers your question, Roland.
In a general way, yes. I had also in mind that I think it might be too complex question right now, but just I'm wondering about it in general, and maybe you have been thinking about it or want to think about in the future, is that I'm wondering what is there some taxonomy of typical simulation mistakes that can happen? Like people have typical mistakes they can have. Maybe there are many of them, but there is still some typology. And similarly, I'm wondering about AGI.
Yeah, interesting. I haven't thought much about that. I think the thing I'm pointing out here mostly is that you can have accurate simulations or that can be used to do some like have some kind of consistent, kind of aligned directed action. But the issue here is about, are these simulations comprehensive enough? Do they cover the span of possible effects happening throughout the environment over time? So in that way, I'm basically just talking about not as much as like, hey, where will there be specific mistakes and there are definitely issues there, and also questions around like if it happens to be the case that the simulator inside this control system connected within the AGI is wrong somehow, like how are you going to correct for that? Are you going to have some kind of system on top of that kind of trying to correct the simulator? And like, how do you know that that system is not actually broken or wrong somehow? So you're going to like have something on top of that. So there are definitely questions around that. But what I'm more pointing to is that like whatever simulator you have, like whatever is kind of running some kind of model of an environment that includes the AGI, it's just going to be woefully incomprehensive, incomplete. Yeah, which I can dig into more in terms of why that would be.
Maybe one more variation of the question is that are there any activities or actions that the AGI could do a bit more safely with slightly higher probability of having correct simulation, or at least having better chance of detecting the mistakes in such manner that it is able to correct? Because, for example, control systems, they are never perfect, but they also have ability to correct unless the system becomes too unstable. So, for example, if you are driving bicycle, then you are swerving all the time slightly, but if you are too much already like out of balance, then you only fall. And similarly, maybe with AGI, that maybe some actions are safer, and then I'm wondering what are the conditions where the AGI can still take some risks and correct them later, and what are the conditions where it should rather not do things.
Yeah, let me see, that makes sense. I mean, like one obvious thing to point out here, which we can already do with large language models and deep neural networks, is that if you can constrain, like adding constraints or like scope what the system can do. For example, you can constrain the inputs, you can constrain the outputs, you can constrain like the domains, the context where it's used. Then the system, like, yeah, is less able or has less potential of causing destabilizing effects because you're restricting it. Having said that, if we're talking about the way I'm thinking about AGI, given how corporations will be acting, given how they will be using these AI models to not only automate information work, as we've seen with generative AI, but also physical work of robots, moving things around. But finally, also it just makes sense to start automating the work of like reproducing the robots, because then you have more robots to do more work over time. There's that kind of economic dynamic. And honestly, I think that for some definition of AGI or ASI, I think at the very least it would be reasonable to expect the system to be able to maintain its own components and to be able to operate over a longer period of time without humans in the loop. So, but in that case, we are talking about a system that will be producing its components and directly, and you can have these kind of yeah, it's basically reproducing itself. These clusters of components are kind of interacting with each other in ways that can reproduce themselves. And they're basically a population of nested and connected components. And once you have something like that, evolutionary selection will creep in. There will be selection for like whatever works, for whatever components happen to interact in ways that happen to lead to effects that were needed for them to continue to exist, or to exist more, or to kind of discover new kind of larger connected functionality that allows either of that to happen. And that will happen. And the thing is with evolutionary selection, I think sometimes people think that you can have something like a machine learning to overcome evolutionary selection. But the thing is that evolutionary selection is like super comprehensive. It's basically happening across all of the interactions that all these components are having with each other and a larger environment over time. It's basically just like distributed A/B testing everywhere. It's like just trying like empirical kind of testing across the board. So on that, like it's slower than like machine learning is, because machine learning can be much more directed. But machine learning cannot be used to simulate or create models to simulate all of those things going on. And in that way, it's whatever control system that you're going to have that's going to make use of that model, that learned model, is just not going to be complete enough in terms of its coverage of what could be evolutionary selected for over the environment. And so basically what I'm saying is, like, if you have something like that, like we can talk all about like maybe the machine can learn to like be more safe within these particular contexts. But if you have that kind of runaway feedback loop of evolutionary selection, like whatever is kind of happening there more abstractly, it is not going to be able to contain what's happening bottom up, and it's actually happening basically like the evolution, like the machine can learn stuff, and evolutionary selection can even like be kind of co-opting or repurposing the functionality in ways that the machine itself cannot actually properly anticipate. And the other way around, like evolved for kind of connected components could end up kind of forming the basis for kind of intentionality of the machine. I think I'm talking for a lot. Let me see who else has questions or things they want to discuss. So please also just give your own opinions. I've been talking a lot. Yeah, David James, key question, how can a control system prove the control agent if the control system cannot model the agent? Yeah, something like that, where like what I'm trying to point to here is yeah, like the agent is like, what we're calling agent here is actually being modified through interactions over the time in the environment. And yeah, the model is not able to track all that shit happening. And not, yeah. My conclusion, AGIs will be uncontainable in terms of the effects it has. Could very, very easily, even initially, kind of start causing destabilizing effects. And if you have some system like that kind of persists in autonomous ways over time for long enough, it will get evolved to bring about an environment needed for the components to continue to exist and to survive and to reproduce for longer. But will be very toxic for us human beings. That's actually a separate argument. It's an argument about like these AGI systems will actually need different things than we humans do. But even if you just remove that part, we can see how if this AGI is already uncontainable, if it already cannot even contain its own effects sufficiently, that you don't want to be building such a system. Like by the precautionary principle, by the fact that there's a lot of waste, there's way more ways to break like this complex, rich society and ecosystem that we're part of than to like foster its life supporting functionality. We should just not be building something like that because we cannot actually contain it. And even any kind of control system that even AGI could kind of embed within itself cannot even contain the effects, the feedback effects that it would have in interaction with the environment over the long term. So that's my conclusion there. Yeah. What constraints can be imposed on an agent such that it remains modelable? I think I'm trying to see. Again, the question is like, sure, you can try and we can have models of each other, for example, and like the system can have models of itself, but is that going to be comprehensive enough in terms of dealing with something like evolutionary selection? that is happening. That's mutual, like a kind of mutually reinforcing machine learning and instrumental convergence as well, that can be brought about from assistant learning to optimize. And I'm saying like that's not really doable. You can't do that. Yeah, self-modification seems to undermine any hopes of the above constraints. Yes, but that's what I'm saying. The difference here between like a static neural network and AGI, quote unquote, is that AGI would just be interacting with all, like it's supposed to be generally operating, it's supposed to be generally functional. It will be interacting with all of these different domains and taking inputs and combining them and using them in various ways and learning from them, so therefore causing changes to self, and then also causing outputs that can feed back again. And once you have a system like that, that's also reproducing its own parts, you have these direct evolutionary feedback loops as well. And yeah, then you just have runaway feedback loops or runaway kind of changes in functionality that the system itself cannot actually properly anticipate and constrain for. And we definitely can't build a control system for initially to constrain for. Agent self-modification into a particular representation format, such as a particular virtual machine. I don't, that's not how I'm thinking about it in terms of AGI. If we're just talking about a virtual agent, like an NPC, then I don't really, like, it's not general in terms of how it functions. Like then we're just talking of, yeah, maybe we're using different, thinking about different problems there. Yeah. Jacob's question around, has there been much mathematically rigorous studies on limits of alignment and controllability, or has it been more a proof of concept so far? Good question. And I could also see that in terms of how I gave this talk, which was more like summarizing that question gets asked. So let me see. There's levels to this. Like one I would point out is Roman Yapolsky has some nice kind of overview papers, which basically saying, like, hey, here's a bunch of things that we can say AGI will not be able to control for, or we would not be able to control for building such a system. So like look up Roman Yapolsky. There's like the impossibility results in AI. And I'm just recommending this because there's not been much, there's been very little coverage of this in the alignment community. Like Roman has also mentioned to me that he's noticed in the past that he might talk about his papers and people even nod their heads, and then the people just kind of go on like nothing happens. They don't really. There's not a lot of probing of like, okay, what does this actually mean for like limits to what we can align for, and there's not a lot of engagement. And I think partly that has to do with like how this community started or was founded, which was like a lot of emphasis on, yes, we should be able to solve this problem. This must be a solvable problem. Like we'll resolve ourselves to solve alignments. And I think it would have been better to spend more time initially kind of scoping out the problem and looking for potential impossibly proves by contradiction that shows that like actually alignment's not going to be tractable, or it's actually just theoretically not solvable. So that's one thing. Roman Yapolsky's work, he's got a lot of different papers on, but it's a bit grab baggy. It's kind of more like you can look at each of these things and kind of get a picture of like, okay, that doesn't look like it's going to work. There is other work here by the ex-Pentagon engineer that they're trying to formalize what I call the hashiness model, which I think is a very nice and simple, like the most simple version that the ex-Pentagon engineer could come up with. That was conveyable, and I'm hoping, and this is, I don't want to push him online. I hope he's actually working on mathematically formalizing that right now. I think that there are ways of being precise about things like I just mentioned, the question around the completeness and consistency trade-offs, and a question like how do you think about evolutionary selection as in terms of being this particular kind of process that happens through external interactions that feedback, and can that be contained? The difficulty here is like I I can't really convey this well. I've done a lot of work. I've like written that post, kind of trying to get to it, but I can't really convey it in like 20 minutes. And I feel like I've been taking some of the bridge builder role here as well, where I have enough of an understanding of this where I'm basically convinced, like I've probed enough for these arguments, but I can't really kind of use maths or kind of like I feel like this is something that actually would be good for someone like Anders or others to actually put into some kind of formal annotation of reasoning that would be convincing even for people who might be somewhat motivated against hearing things like this. Yeah. See, mentioned something else, but I didn't get the spelling right. Yeah, I'm just deliberately not really mentioning ex-Pentagon engineer because he wants to just live a quiet life right now. But I'm waiting for Anders Sandberg basically if he's interested, or to maybe work on formalizing that if he gets around to it. Yeah, you can also take a look at the outline I wrote before that gets a bit more precise in terms of what we're dealing with of the control problem. I would recommend people to start thinking this through themselves. Like, don't wait for someone to create like a very neat mathematical thing. Like, that's not what happened in the rest of the alignment community. So in that sense, I think we need to apply even standards here, as we should have done from the get-go, and actually consider reasons why it might actually not be possible to align AGI to stay safe, and to actually consider those reasons seriously. Yeah, anything else? Any thoughts, any questions, any points? See, we have 4 minutes left.